Alright, so number 13 here, a rectangular area is to be enclosed by a wall on one side and fencing on the other three sides. If 18 meters of fencing are used, what's the maximum area that can be enclosed? This is a little bit of calculus esoterica, but we did problems like this back in, I think it would have been in chapter 5. Section 5 something, 5.7 or 5.8 maybe, applied maximum and minimum problems. So the thing is, we're trying to find a maximum, so we definitely want to have like a function, maximum of area. So we want to have an area function that I can then take the derivative of and set it equal to 0 and do all that. So let's see if we can do that. Well, if I called this side x, and this side x, then, and if I've got 18 meters of total fencing, then how much would I have left for here? Well, I've got 18 total, and I've used up 2x so far, so this would be 18 minus 2x. So the area is 18 minus 2x times x. It's the area of that rectangle. So that's 18x minus 2x squared. If I'm trying to find a maximum, I need to take the derivative and set it equal to 0. Derivative of this is 18 minus 4x. So where is that equal to 0? That's equal to 0 at x is equal to 18 over 4, or 9 halves. Now, be careful. That's an answer here, but what are they asking for? They're asking for what is the actual maximum area, not what's the x value that gives you the maximum area. They want to know what's the maximum area. Well, I've got my area function right here. So let's go ahead and just plug the 9 halves into that. I'm going to use this factored form. I think it might be easier. So 18 minus 9 halves times 2 is 9 times x, which is 9 halves. So that's 9 times 9 halves, or 81 halves. So that's E. Number 14. So this thing is the 4th degree Taylor polynomial for a function f about x equals 0. What's the value of the 4th derivative at 0? Well, remember the recipe for making a series. This is at x equals 0. So the recipe is it's f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial, and so on. And the 4th degree term is the 4th derivative times x to the 4th over 4 factorial. Or, maybe more suitable for this, you can move this here, so it's the 4th derivative at 0 over 4 factorial times x to the 4th. That's how you make a series, and that's not negotiable. So this thing right here, that must be equal to 6. This must be equal to that 6 there. So that means the 4th derivative at 0 over 4 factorial, which is 24, must be equal to 6. So what's the 4th derivative equal to? Well, I guess it's 6 times 24, which is E. So that's about knowing this recipe, just understanding that you need to set that equal to that. All right, suppose natural log x minus natural log y equals y minus 4. And this, what's the value of the derivative when x equals 4? Well, this is a derivative. I don't think we want to try to solve this for y. I don't know if we could. So we're going to use implicit differentiation. That just means we're going to charge through and take the derivative. But every time we take the derivative of something that has a y, a dy dx pops out. So what's the derivative of natural log x? 1 over x. Derivative of natural log y is 1 over y times dy dx, because there's a y. What's the derivative of y? Well, I guess it's like 1, but dy dx pops out, and then the derivative of minus 4, that goes away. It's just a constant. So they want to know what's dy dx when x equals 4. Well, they told us when x equals 4, y equals 4 also. So that's 1/4 minus 1/4 times dy dx equals dy dx. Sorry that you have to do algebra here, but that's the nature of the game. I need to add this to the other side. This is a whole dy dx plus 1/4 of a dy dx is 5/4 of a dy dx. And then if I divide this over to the other side, dy dx is equal to 1/4 over 5/4, which is the same as dividing by a fraction, like multiplying by its reciprocal. That's 1/5. Implicit differentiation. That is section 4.1. Not hard to do. It's basically just like the chain rule. Every time you take the derivative of something with a y in it, you have to multiply by the derivative of what's inside, which is dy dx, because it wasn't an x. All right. Let R be the region in the first quadrant that's bounded by the polar curves r equals theta. So r equals theta is this spiral, would spiral out like this. The r is equal to the theta, so the bigger the angle gets, the further out you go. And then theta equals k. So if theta, the angle is a constant, that's just going to give you a straight line like that. Okay, so that's which one is which. This is theta equals k, and then this one here is r equals theta. What's the area of this in terms of k? Well, area of a polar curve, formula you need to know, it's 1/2 the integral from theta 1 to theta 2 of r squared d theta. Right? So let's think polar here for a minute. Where am I looking from? I'm looking from here, from theta equals 0, up to here, and that's where theta is equal to k. So I'm looking from 0 up to the angle theta equals k, right? And then r squared, well, r is equal to theta. So it's pretty easy calculus from here. The antiderivative of theta squared is theta cubed over 3 from 0 to k. And if you plug k and 0 in, and I think you will find that it is k cubed over 6. All right, which of the following is the series for e to the 3x? Well, e to the x, that's one of the big 4 that I'm supposed to know. That's this. Sorry, that's supposed to be a 2 there. And so on. So e to the 3x is just putting 3x in place of the x's here. So 1 plus 3x plus 3x squared over 2 factorial, and so on. And let's see, they don't have things in parentheses, so I'm going to have to do just a small bit of simplifying. So this is in parentheses, so that 3 is getting squared. So let's see. Looks like here. Looks like E is the one that matches up. Right? And again, like when you see this, scan over the answers, you might see this and go, wait a minute, That looks familiar. That's just the series for e to the x. But I need to plug 3x in for the x. Not too bad. Need to know the big 4. We'll stop this one here.